Hi everybody, welcome back. In the last video, we looked at some of the violations of the classical OLS assumptions. And in this video, we're going to elaborate on the last one, which was our assumption of no endogeneity. And that can be violated through a couple different means, which we're going to talk about in this video. So we're gonna discuss the violation, coming from simultaneous equations and omitted variables. Let's start with simultaneous equations. Okay, so a simultaneous equation in econometrics is basically a feedback loop. Between x and y. And let me show you this by actually writing down a couple equations here. So suppose that we have our equation y is equal to beta 0 plus beta 1x plus, actually I'm going to give a little room here, plus epsilon. Okay, so that could be fine and true, but let's suppose we also have x is some function. So we just have, instead of beta, I'm going to use alpha as different parameters because it's a different relationship. So x is a function of y plus epsilon. This is a common thing between supply and demand. Supply is a function of demand, and demand is a function of supply, price, and quantity. And so, like y could be price, and x could be quantity, for example. And the quantity supplied or demanded is going to be a function of the price, but the quantity supplied or demanded is also going to be a function, or sorry, the price is also going to be a function of the quantity. So quantity is a function of the price is a function of the quantity. So what does this mean, and what does this look like as a simultaneous equation? So let's suppose there's a random shock to y coming through the error term that's not explained by any changes in x. It's a random shock. So if the error term and x are correlated, well, first of all, if this is the first thing that's happening, if epsilon goes up, that means y is going to go up because it's plus epsilon. So y is going to increase by whatever that shock is. Okay, y has gone up, but now what happens here in this second equation, since y has gone up, well, y goes up there too. And if y goes up here, we have plus alpha 1 y. That means that x is going to go up. So x goes up. That's kind of the fourth component of this. And if x goes up there, well, x goes up here too. And that's number 5, right? And so essentially what this is showing that is that the error term is correlated with x. Because if the error term increases, it's going to increase y, and that's going to increase x, and that's going to increase x back in the original equation. So these are correlated with each other. That means we have the problem of endogeneity. And again, if you wanted to think about that in more economic terms, you could think about y as price, and you could think about x as, for example, quantity demanded or quantity supplied if you wanted to. Because these are going to feed off of each other. Okay, so we have this endogenous relationship between x and y. epsilon, the error term, is correlated with x through the simultaneous equations. And so what's that going to do? That's going to mean that beta 1, the effect of x on y, the estimate of beta 1 will be biased. And in this case, downward. And also, or well, not also, but to kind of clarify, that's going to mean that OLS, ordinary least squares, would mistakenly attribute the variation in y, little y, created by the error term, created by ultimately the shock to the error term, and it's going to mistakenly attribute that to have been caused by x. Okay, because x is going to go up. It's going to look like, it's going to look like x increased, and that caused an increase in y. But it's the shock, it's the error term, the randomness that caused the increase in y, not the increase in x. So beta 1 is going to be biased, and it's going to attribute some of these changes to x when it wasn't x that was actually doing it. So that's what we have going on there. Let me just show a couple of actual examples where this could also take place, and apart from supply and demand type of example. So, for example, you could have income a function of education, right? And so what we're saying here is that beta 1 is saying that if education increases, income increases. But we also do see that people with higher incomes also tend to obtain more education. So there's some simultaneous equations going on there. If we can figure out a good way to measure this, if we're trying to measure the outcome of healthy eating, and we want to see whether time spent working out, if you work out more, if beta 1 is positive, that would say if you work out more, you're more likely to eat a healthy diet. But if you eat a healthy diet, you're probably more likely to work out more as well. So again, a simultaneous equation there. So, and these are a little bit harder to solve than just like plugging in robust standard errors into the statistical package or something like that. We're going to have to do some different types of econometric techniques in order to deal with this. So we'll talk about those. But first, we'll talk about those in future videos. But first, let's talk about the other source. So the first source of endogeneity is simultaneous equations. The second source, and probably an even more common source, is omitted variable bias, or just omitted variables. I'll go ahead and put omitted variable bias. Okay, so let's suppose we have a true model where the outcome y is a function of the constant plus beta 1 x plus beta 2 z plus epsilon. Okay, that's the true underlying model. Y is explained by two variables and error. Okay, but if we leave one of these out, and this could be like what we were talking about in the last video, where if you're trying to explain sales and you're using it as a function of unemployment and of income, yes, unemployment and income are going to be multicollinear. There's going to be multicollinearity. But what happens if you leave one of those out? So if you've estimated y is equal to beta 0 plus beta 1x plus epsilon star. So we're leaving out z. Well, epsilon star then is actually epsilon plus beta 2 times z, right? And if z is at all correlated with x, then E star, our error term in the estimated model, epsilon star is correlated with x. And that's the definition of endogeneity, the error term here being correlated with x. So, and that one's a little easier to see than the omitted variable, the simultaneous equations. If you leave these out, if you leave this out, then both of these get put into the estimated error term. And so if z is correlated with x, well, yes, there's multicollinearity, but if you leave it out, there's omitted variable bias, because now epsilon, the model's epsilon, is correlated with the model's x. So that is this idea of omitted variable bias, and again, that's going to cause a biased beta 1. It's gonna look like the relationship between x and y is either greater or less than what it actually is. Okay, so example here. If we have the true model, if the true model is health is a function of health insurance and income, but we estimate that health is only a function of health insurance, HI for health insurance. If we estimate this and we leave out income, then the estimated error term epsilon star includes income, which is correlated with whether or not a person has health insurance. So the error term is then correlated with x. And so this violates the no endogeneity assumption. And this will bias the estimates of beta 1. Well, the estimate of beta 1. Okay, so instead of having beta 1, normally we want the expected value of the estimate to be equal to beta 1, the true beta 1. But in this scenario, what we're going to have is that the expected value of beta 1 is going to be equal to beta 1 plus beta 2 times alpha 1, where alpha 1 is the effect of z, in this case income, on x, which is health insurance. Okay, and so the regression coefficient of z, if we were building a separate regression equation and we had z a function of x and a totally separate error term. If this is a separate regression equation and we're trying to find out what is the relationship between x and z, well, that's alpha 1. So what's the relationship between health insurance and income? That effect, alpha 1, is going to be captured inside the effect of the estimate of beta 1. So we want the estimate of beta 1 to be equal to the true value of beta 1. But it's not. It's going to be equal to beta 1 plus beta 2 times this extra effect of x on z. And so that's the kind of underlying theory about what's happening and kind of why it's important. But if nothing else, you should just know that if you leave out a variable, it's going to be capturing more effect than you want. So if we have the expected value of beta 1, if I rewrite this, beta 1 plus beta 2 alpha 1. The other way we could write this is that's equal to the true effect, which is just beta 1, plus bias due to omitting z. And if x and z are positively correlated, that is, if that alpha 1 in this regression equation if that's a positive alpha 1, then the bias will be upward and vice versa. So if we're looking at, let's go back to the original, this one. If we estimate this equation here and we omit z, we're gonna find an estimate for beta 1. We're gonna end up with a beta 1 hat. And if that effect is something like 0.5, it might be biased up to 0.7. Because if there's a positive correlation between the omitted variables, beta 1 hat is going to be overestimating the effect. If there's a negative relationship between these two variables, beta 1 hat will be underestimating the effect. Okay, in this case, beta 1 would make it look like beta 1 would have us believe there's a larger relationship between health insurance and health than there actually is, because we left out income. And income is also going to increase our health. Higher income is going to be correlated with higher health. So if we leave those out, it's going to attribute all of that to beta 1 instead of only the health insurance part. So that's why it's really important when you're doing causal econometrics. Yes, you might have your relationship of interest, your beta 1, that's what you're trying to find out. Does health insurance affect health? But to do that, you need to include income, you should include age, demographic variables, economic variables, as many extra control variables as you can think of that also might affect health. Because if you omit them, then you will make it look like health insurance has a bigger effect on health than it actually does. So that's what's going on there. Just about done. And okay, so this bias will exist unless, so 1, the true effect of any given omitted variable is 0. The true effect of any given omitted variable, z, for example, on y is 0. So if income doesn't have any effect on health, then it's okay if we leave it out. That's the idea there. So for example, we have y is equal to beta 0 plus beta 1x plus beta 2z plus e. So the bias will exist unless the true effect of any omitted variable z on y, that's not z1, that's a comma, on y is 0. So in other words, if beta 2, i.e. if beta 2 is equal to 0, the effect of z on y, if that's 0, then it's okay if we leave it out of the equation because it doesn't matter. So that's kind of simple. The other way where the bias may not exist is if the included and omitted variables are completely uncorrelated. The included, so for example, x, and omitted, so in our example z, variables are uncorrelated. So that would be saying, in the way I've been describing it, if the correlation, if, and this is a big if, if the correlation between health insurance and income is equal to 0. If those are not correlated, then that's also okay if we leave out income. It's not going to bias our health insurance coefficient. But if these are at all correlated, we cannot leave out income because that's going to bias our health insurance variable. Okay, so the probability of both 1 and 2 existing is highly unlikely. And this is particularly a problem because omitted variables can also include characteristics or traits that are unobservable or hard to measure. Okay, so things like things we've talked about before in some previous videos, but stuff like motivation, work ethic, ambition, or ability. Right? We try to control for or proxy for these things. We use things like test scores or grades, but those are not going to fully capture the full extent of these types of variables. So unless we come up with really good regression designs, it's going to be hard to find these causal effects because it's hard to control for these unobservable characteristics. So to round this off, with proper design, and that's kind of going to be a key part of what we continue to talk about, linear regression can create unbiased estimates. As hard as it may now seem, linear regression can create unbiased estimates. But the use of IVs, which stand for instrumental variables, regression discontinuity designs, regression discontinuity designs, and what are called difference in difference designs are particularly helpful to remedy violations of this assumption. Are particularly helpful to remedy violations of this assumption. Okay, and so we're going to primarily be using multivariate regression, and essentially what we're doing with that is if we have some y variable and then a whole bunch of x variables, we're going to hope that if we control for enough observable characteristics in the x variables, then by controlling for enough observable characteristics, that's also going to help control for the unobservable characteristics. But like I said, some of these unobservable characteristics are notoriously hard to control for, but then we can start to move to more advanced econometric techniques later on, that's going to really help with helping remedy violations from this assumption. Okay, so endogeneity, it's a big issue, particularly within causal econometrics. But yeah, so now you can understand some of the underlying causes. This is why it's really important to try to control for as many observable variables as you possibly can when you're trying to uncover some causal relationship. Thinking about simultaneous equations as well. But yeah, and so just keep that in mind as we move forward. Whenever you're doing some regression equations, regression modeling, you really want to try to include as many control variables as you can, and you're picking those by either using previous research that has used the variables, or if there's some economic or intuitive reason that they should be included, then you throw them into the model. Even if there's going to be multicollinearity is not nearly as big of a problem as multicollinearity. Heteroscedasticity we can handle, autocorrelation we can handle, but multicollinearity that's harder to handle except for removing variables. But you don't want to remove those variables unless you have a very, very good reason, because it's going to cause omitted variable bias. All right, so just keep that in mind as we start moving into more applied econometrics, into some more of the Python and the coding, that's always going to be an important consideration. All right, so that's going to be it for this video. That's going to be it for the classical assumptions series of videos. And so I will be back in touch with more videos soon with some more information about actually conducting regression analysis. Okay, thanks for watching, and I'll talk to you soon.